So we will start the next presentation, the next lecture. Jean-Charles Billaut will talk about integrated scheduling and routing. So after some routing, we will focus on integrated problem. So I'll let you go.
Thank you, Caroline. So I suppose that some of you are working on scheduling problems, yes? And some of you are working on vehicle routing problems, yes? Okay, so we are discussing now on integrated scheduling and routing problems. The outline of my talk is the following. I will start by an introduction. Then I will give some basics on scheduling, some basics on vehicle routing. And then I will present what an integrated problem is to our point of view. And I will present some possible resolution methods because it's a new problem, so with very few literature. So we cannot say today that some methods are well known to be better than others. We will see. And then I will conclude. And tomorrow, for those who will be at the project-based learning project, we will implement a mathematical programming model with GLPK. Maybe you have received the link to download the software. And you will work also on Python. I hope that you know Python. It's not difficult to learn Python if you don't know. And we will see. Okay. So I start with the introduction. First, some definitions. What is a scheduling problem? It's the allocation of scarce resources to tasks over time with respect of some constraints and the goal of optimizing some objective function. It's a very general definition. Maybe you will have the slides after, I don't know. Caroline, there is a website where you will put the slides? Yes? Okay, so you will have them if you want. What do we have? We have a set of jobs. We denote the set of jobs by J, G1, G2, up to Gn, to be processed on a set of machines M, M1 to MM. And the objective is to find a schedule. It means a starting time for each job and a performing machine, satisfying some constraints, and optimal with respect to some criteria. The representation of a schedule is generally done by what we call a Gantt chart. It means we have the time axis and the job, which are put the one after the others, and the length of the job is the processing time of the job, the duration of the job. What is a traveling salesman problem? We have a collection of cities and the cost of travel between each pair of them. And the traveling salesman problem is to find the cheapest way of visiting all of the cities and returning to our starting point. So we have cities, we have matrix of transportation costs, and we want to find a tour visiting all the cities exactly once, and with a minimum transportation cost. I suppose that you know this. And the vehicle routing problem, also you know what it is. The problem is to find an optimal set of routes for a fleet of vehicles to traverse in order to deliver a given set of customers. And it is a generalization of the traveling salesman problem, sorry. So we have vehicles, depots, road network, cost, customer requirements, and we want to find a route in order to satisfy the customers and to minimize the total cost. So why is it important to solve scheduling and vehicle routing problems? It's interesting first from a theoretical point of view. When we do research, we like theoretical problems. So it's interesting from this point of view. And it is also interesting from a point of view of applications. For scheduling problems, we have, of course, production problems, production optimization problems, but also crew scheduling, staff scheduling, project scheduling, operating room scheduling, etc. A lot of scheduling tasks to solve, and very important from a practical point of view. And for the vehicle routing problems, of course, as you know, logistics, urban logistics, garbage collection, school bus planning, etc. A lot of applications of vehicle routing problems. So both problems are very important from the point of view of applications and theory. So the question is, why is it important to consider integrated problems, and what is an integrated problem? I will show in section 4 the integrated problems, but why is it important to consider this sort of problems? In most of the cases, scheduling and vehicle routing are two problems considered separately. The scheduling problem is solved, the products are terminated, and generally we don't care about their delivery to the customer. It's a problem of the 3PL provider, and we don't care about it. And if we consider the vehicle routing problem, we don't have any consideration on how the products have been produced. The only problem that we consider is the delivery. And the production is the problem of someone else. We consider that production and delivery are strongly connected. It means that jobs, in the case where jobs are produced continuously, they have to be delivered to the customers within strict time windows, and vehicles arrive continuously to deliver the produced jobs. And in this case, production and delivery have to be solved together. The schedule has an impact on the job's release, and the routing has an impact on the delivery time and on the date the vehicle comes back to the production center to deliver again new jobs. So the two problems are connected in this case. I start now with some basics on scheduling. For people who know, I'm sorry, it's very basic results. For people who don't know, maybe you will learn something. First, I start with some notations, very common in scheduling. The classical notations are the following. First, the data. We denote by n the number of jobs. Pj will be the processing time of job j, so the duration of the job. Wj is a weight. The weight is a way to make a distinction between jobs. So in the objective functions that we will see, we can put an important weight for jobs who are important and a small weight for jobs which are less important. Dj is the due date of the job. So it means the date at which the job has to be terminated, completed. And we have variables. In fact, the variables depend on one variable, which is the completion time of the job. The completion time of the job is the most important variable in the problem. It's equivalent to the starting time, because completion time minus processing time is equal to starting time in this sort of problem. We have the lateness, Lj, the algebraic tardiness of job j, the difference between the completion time and the due date, the tardiness, which is the maximum between 0 and this quantity, and uj, which is a Boolean indicator, which is equal to 1 if the job is tardy and 0 otherwise. These are the most common variables in scheduling problems. Of course, we can imagine other variables, but for the basics on scheduling, it's enough. The elementary constraints that we always have in scheduling problems is that one job is executed on only one machine at a time, and one machine can perform only one job at a time. Of course, sometimes we can imagine that a job can be performed by several machines at the same time. It's a very specific case. And we have also machines that can perform more than one job at a time. It's also a very specific case. For general problem, basic problem, one job at a time, and one job at a time is performed by a machine. The objective functions, because we want to define a starting time for jobs which are optimal for some objective functions. We have the most common, the most famous maybe objective function, which is the make span, the maximum of the completion time. It means that we want to complete, we want that the jobs who completes at the maximum date is minimum as possible. So we want to minimize the maximum completion time. We want to minimize also the weighted total completion time, weighted or not weighted, the maximum tardiness, the sum of tardiness, which is the total tardiness, total weighted tardiness, etc. And also the total number of tardy jobs, or total weighted number of tardy jobs. These are the very common objective functions in scheduling. And in scheduling literature, we use generally a notation for problems, which is a 3-field notation with alpha, beta, and gamma, 3 fields. where alpha denotes the machine environment, beta denotes the specific constraints of the problem, and gamma is the objective function. So for machine environment, I will give examples just after this. Machine environments are the following. First, I distinguish here the machines for independent tasks. So I have jobs to schedule, and the jobs are independent. So single machine when there is only one machine, and parallel machines when there are several machines which can perform a job, but we can choose a machine among the set. PQR means that the machines are identical for P. Q means that the processing time of the job depends on the machine, and R means that the processing time depends both on the job and on the machine. And we have also workshop environments. And workshop environment is not the same. Here we have flow shop, job shop, or open shop. A flow shop means that the jobs follow the same route in the shop. So all the jobs pass on machine 1, then machine 2, then machine 3. For job shop, it's the routing of the job. It's a routing of jobs. It means the route of the job in the shop. It's not the route of a vehicle routing problem. We will talk in a few minutes. It's something else. But it's also the route of the job, depends on the job. And open shop means that the routing in the shop is open, not pre-specified. The Gantt chart is the notation, is the usual representation of a schedule. Here you see a schedule of a flow shop with 3 machines, job 2, job 1, job 3, in this order on machine 1, in the same order on machine 2, and in the same order on machine 3. It's on the left, it's what we use in our papers generally to represent a schedule, and on the right it's a Gantt chart also, but in an industrial software, which was developed by some of my PhD students more than 10 years ago for the workshop working on the production of paper production. Examples. This is a single machine problem. You have only one machine with 3 jobs. 2, 1, and 3 is the sequence. Okay, just to illustrate. Parallel machine problems, we have 2 machines, M1 and M2. I didn't put the name of the machine, but anyway. And on one machine you have jobs 2 and 3. On the second machine you have job 1. Here you can see that the jobs are independent. Okay, one job is one operation. And for flow shop problem, we have also 3 jobs, but 2 machines, and one job is performed first on machine 1 and then on machine 2. For job shop, here we have a job, oh, there is a mistake, of course. The last version was done yesterday, okay, so there is a mistake because job 1 cannot start on machine 1 before it completes on machine 2, because the routing of job 1 is machine 2 and then machine 1. And the routing of the other jobs 2 and 3 are first on machine 1, then on machine 2. Okay? Everybody has understood the error in the slide? It's a good way to see if you understand. Okay, now maybe a last definition of a particularity. It's a permutation flow shop. What we call a permutation flow shop. Here in this example you can see a flow shop schedule. It means all the jobs are scheduled first on machine 1, then on machine 2, and then on machine 3. And the sequence on machine 1, 2, and 3 are not the same. Okay, but it's a flow shop. Maybe it's not a good solution. Okay, but anyway, it's a flow shop. What we call a permutation flow shop is a solution where all the jobs have the same routing, but also the order of the jobs on the machines is the same on all the machines. So for all the jobs, they pass first on M1, then on M2, then on M3, and they do not cross up together. Okay. So if we start with job 2 and then job 1 and then job 3, it's the same order up to the end. We know, what do we know? So it's a permutation flow shop. And we know that for the make span minimization, so if we want a schedule that completes as soon as possible, this sort of flow shop is dominant up to 3 machines. It means that if we have a flow shop with 3 machines, we can focus on permutation flow shops, and we are sure that we will have a solution, if we obtain an optimal solution, which is optimal for any schedule. But for m equal to 4 machines, then permutation schedules are not dominant. It means that sometimes it may be interesting to switch 2 jobs in order to minimize the max span. Okay? I wanted to give you an exercise, I don't know if you have the time, to find such a schedule with 2 jobs. Okay, you will do it at home or not. Another remark is that the flow shop, the max span, is given by the longest path in a graph. So if you consider this flow shop, and if you build this graph with 1 node per operation, and on the horizontal line you have the resource constraints. On vertical lines you have vertical arcs, you have the routing constraints. And in fact, if you associate to the arcs the durations of the operations, computing the longest path in this graph is equivalent to find the starting times of the operations and so the max span of the schedule. So computing the max span of a schedule in a flow shop, in any schedule in fact, is equivalent to compute a maximum longest path in a graph. Any question up to now? Okay, examples. On the left, problem is 1 sum of completion times. It means that we have only 1 machine, and we want to schedule the jobs in order to minimize the sum of completion times. I consider 5 jobs with processing times 8, 5, 3, 7, 2. The question is, what is the optimal order? What is the optimal sequence of jobs? You have 2 minutes. Yes? Sorry? Any sequence? No. Any sequence is optimal if you want to minimize the max span. The max span is the total duration. Of course, in this case, good. I didn't think about it, but it's a good idea. Next time I will introduce this. For the 1 machine, and Cmax objective function, it means that you want to minimize the max span, the total max span. There is only 1 machine. You put all the jobs on the left, and of course, any order completes at the same time, which is the sum of processing times. So there is no problem here. It's a no problem in scheduling. It's a joke for scheduling people. So here you want to minimize the sum of completion times. Okay, so you compute the completion time of job 1 plus the completion time of job 2. You make the sum, and you want the sum to be minimum. The smallest first, and then the others. Yes. You see the animation? Yeah. I'm a boss with PowerPoint. Yes, it's optimal. You put the jobs in this order, and this is optimal. Yes, you're right. And so you think that this problem is easy or difficult to solve? Easy means polynomial. I suppose that you have basics in complexity theory. So this problem is polynomially solvable or not? Yes, it is. Okay. And for the second one, you have 2 processors, M1 and M2. And you want to schedule the 5 jobs, the same jobs, on M1 and then on M2 in order to minimize the max span. So, any idea? So here, for example, you can put job 4, job 1, then I don't remember, job 2, 3, and 5. And the max span is equal to 13. Okay? And to your opinion, this problem is easy or not? Yes, it's not easy. It's a difficult problem. It's a partition problem, in fact. Yes. Exactly. Ordinary NPR problem. Okay, here now I consider a two-machine flow shop. So we have two machines with these jobs. So 8, 5, 3, 7, 2 are the processing times on first machine, and 3, 6, 5, 2, 4 on the second machine. I put here a solution with max span equal to 30. The question is, do you have an idea of a better schedule? Maybe it's more difficult to imagine it. Yes, I will introduce it in few slides. Thank you. Je me fais casser. Oh, I don't remember. Yes, here is a solution with the same instance with a max span equal to 27. So it's better. So, and do you think that this problem is easy or not? Except for people who know the basics on scheduling? Yes, if you if you learned it some years ago, please don't answer. If you discover scheduling, what is your idea? Is it difficult or not? No. Okay. No, it's not difficult. For this problem, it's polynomially solvable. And we will see the algorithm. And now two parallel machines, M1 and M2. If you remember, we wanted to minimize the max span. We said it was difficult. Now we want to minimize the sum of completion times. And you think it's easy or difficult? In between? Now it's easy. It's easy. You sort the jobs in increasing processing times, and you put them machine 1, machine 2, machine 1, machine 2, etc. And it's optimal. So you have the sum of completion time for this example equal to 37. So as you can understand, scheduling is a huge family of problems. And you have to know a lot of things on a lot of problems, in fact. So maybe I can skip these slides, 2 slides on complexity. I suppose that you know what is polynomially solvable, what means P, NP, etc. So I switch these 2 slides. Okay. So first results that maybe you have to know if you if you have only 1 hour and 30 minutes of course, is that minimizing the maximum lateness is polynomially solvable. And the algorithm is to sort the jobs in EDD order. EDD means earliest due date first. So you start by the jobs with the smallest due date, and then you continue up to the job with the maximum due date. It's very intuitive. Minimizing the sum of completion times, we have seen this on an example. It can be solved optimally by sorting the jobs in SPT rule. Okay, SPT and EDD are very famous rules in scheduling. So I think you have to keep these rules in mind. And sum of completion times is sometimes what we call the work in process. Maybe you have heard about work in process. It's the time during which a job is in the shop. And if we imagine a shop, maybe a very complicated shop, jobs have what we call release dates. It's the time at which the job enters into the shop. The job is completed, I don't know where, somewhere here. And the time during which the job is in the shop is the completion time minus its release date. And sometimes we want to minimize this quantity in order to have a workshop with as less as possible jobs in process. So we want to minimize this sum. And because we want to minimize this sum, and because the release dates are data and not variables, it is equivalent to minimize the sum of completion times. So minimizing the sum of completion times is also minimizing the work in process. And you can understand it if you have a lot of things to do. You start with the smallest things that you can do in order to to complete as most as possible tasks, and you keep the longest task for the end. Okay? If you add deadlines or due dates, it's more complicated, but okay, it's intuitive. Sum of WGCG, so weighted completion times, it's a ratio. So I write here the proof. I can do the proof if you want. Very quickly, maybe. You consider a schedule. It's very simple example. With a partial sequence sigma, a job I, a job j, and a partial sequence p. And then you consider a schedule S prime, which is exactly the same, but you switch I and j. So you have this sequence with sigma, j, I, and p, pi. And the question is, what is the condition? What can we say? Sum of Cg of S less than or equal to sum of Cg of S prime, if and only if what? So what is interest to put I before j? And if you do this, we can compute here. We have this date, which is C sigma. Here we have the same date. Okay, the total duration of sigma ig is the same as sigma gi. It does not depend on the order of I and j. So this is equal to the sum of completion time of the jobs in sigma plus weighted completion time. Maybe I can put the weight, it's the same, plus the weighted completion time of job I, which is equal to wi c sigma plus pi, plus the contribution of job j, wj c sigma plus pi plus pj, plus the total weighted completion time of the jobs in pi after sigma ij, okay? And this is less than or equal to the same quantity for S prime plus the contribution of job j plus the contribution of job I plus the contribution of the jobs in pi. So we can simplify like this. Then we have WGCG, WGCG, WGPG, WGPG, WIC sigma, and WIPI. And at the end, you have WJPI less than or equal to WIPG. And we say PI divided by WI less than or equal to PG divided by WG. It's what we call the WSPT rule. So it's the same rule as for sum of completion time, but with the weight. So it's the processing time divided by the weight. Okay, so you sort the jobs in this increasing order, and it's optimal. Okay. It was easy. That was the easy part. Now, suppose that I want to minimize the number of tardy jobs. I look at the time because I can talk during 5 hours easily on scheduling problems. Maybe I have to go faster. Okay, this problem is polynomially solvable. P sum of completion time, we have seen it. It's optimally solvable by this algorithm. With a job shop with only 2 jobs and M machines, it's a very beautiful problem, which is solved by geometric approach and computation of a shortest path in a geometric approach. Very, very nice. We have not the time. 2-machine flow shop with max span minimization. It can be solved. We can do the proof by using the same technique. It's a bit more complicated, but it can be done easily. And in fact, we can prove that it is optimal to schedule job I before job J if we have this condition, mean of PI1, PG2 less than or equal to the mean between PI2, PG1. It's what we call Johnson's rule. Okay, I don't make the proof. But the idea of the algorithm is to put at the beginning the jobs with a small duration on machine 1 and long duration on machine 2, and at the end, the jobs with a long duration on machine 1 and small duration on machine 2. Exercise. We don't have time. Okay. It's your chance. Okay, so we have to know a lot of things. About difficult problems, minimizing the total tardiness is difficult. Minimizing the weighted number of late jobs is difficult. Minimizing for parallel machines the max span is difficult. These problems are ordinary and PR'd, and generally we solve these problems by dynamic programming. And for one release dates, Lmax, or total weighted completion times of 3 machine flow shop with max span minimization, or 2 machine flow shop with total completion time minimization, the problems are strongly NP-hard, and the difficulty to solve them is not equivalent. For the first problem, 1 machine, release dates, and Lmax, we can solve to optimality instances with thousands of jobs, no problem, very quickly. But for the last one, 2 machine flow shop with total completion time, up to 50 jobs maybe, no more. So very, very different problems. And on the right, it's what we call a rejection tree. It means that there is an arc between 2 boxes. If, for example, Cmax, Lmax, there is an arc, it means that if the problem with Cmax is difficult, then the problem with Lmax is difficult. And reversely, if the problem with Lmax is easy, polynomially solvable, then also it is the case for the problem with max span minimization. Okay, there are some possibilities of MILP modelization. Maybe I can present. Okay, you know there are a lot of solvers now that can solve integer programming formulations, so it's always interesting to test them. The first model that I present uses positional variables. The data, so I focus on the 2 machine flow shop with total tardiness minimization. The data are the number of jobs, the processing times, and the due dates. We define positional variables. It's a very common way to model a scheduling problem with xgk equal to 1 if job j is in position k and 0 otherwise. And then we use continuous variables, which are the completion times of the jobs on the machines. The tardiness of the job in position k is tk. And if we use this sort of variables, the processing time of the job in position k becomes a variable. It's equal to the sum of pij times xgk. Of course, we have that sum of xgk is equal to 1. There is only one per line and per column. Okay, so the sum for j is equal to 1 for any k, and the sum for k is equal to 1 for any j. And then, with this hypothesis, we have here the processing time of the job in position k on machine I. The due date becomes this variable. And then we can give the expression of disjunctive constraints. It means that the completion time of the job in position k is greater than or equal to the completion time of the job in position k minus 1 plus its duration. And the routing constraints, the routing, I quote routing, it's routing in the shop, not vehicle routing, means that the completion time of the job on machine k is greater than or equal to the completion time of the same job on machine machine A, sorry, on machine A minus 1 plus its processing time. We start with this. The tardiness is the completion time of the job on machine M minus its due date. And the objective function is to minimize the sum of tardiness. Okay, so it's very easy. I think it's the model that I sent you yesterday. And if you have installed GLPK, you have tested the model. I think it was with this. Oh, no, it was with other variables, maybe. It was with linear ordering variables, where here we use variable yjj prime equal to 1 if job j is before job j prime and 0 otherwise. And with this sort of variables, we have Cij, the completion time of the job, Tj, the tardiness of the job. Here, we don't talk about positions. We deduce the positions from the variables, but it's not explicitly in the variable definition. And we use what we call a big M to describe the disjunctive constraints. Using a big M is not good in a model, mathematical model, because relaxations are not good. If you put all the variables continuous, it gives very poor relaxations. So it's very difficult for the solvers to solve such models. But here, we can give the expression of disjunctive constraints. It's a way to linearize, in fact, some quadratic constraints. The routing constraints, starting with this, and the tardiness is this expression, and the objective function is this expression, and I think that this is the model that I sent you, and that you can test with GLPK. Okay, we can also propose models with time-indexed variables. I didn't put the detail, but we have several ways to define time-indexed variables. xgt equal to 1 when job j starts at time t, or when job j is processed at time t, or when job j has already started at time t, etc. All these models are equivalent. And in fact, these models have a pseudo-polynomial number of variables because it depends on t. T is a time index, which depends on the completion time, maximum completion time, which depends on the processing times of the jobs. So if you have huge processing times, you have a huge number of variables. So most of the time, it leads to not very efficient models. Okay, so you have GLPK, I think with this file, which is a model, this file with data, then you obtain a file, an output. If you redirect the output in a file, and from this file you can see the values of the variables and deduce the solutions. Okay, we will see this in details tomorrow. So for this instance, with 10 jobs, we have the sum of tardiness equal to 480. So GLPK can solve instances with up to 10 jobs in some seconds. There are some heuristic algorithms for the flowshop problem. À quelle heure? 19h45. Okay. Okay. Three heuristics. The first heuristic is CDS, Campbell, Dudek, Smith. It was in 56 maybe, 70. Management science. Okay, Campbell, Dudek, and Smith. What is the idea of this heuristic? So we have a M machine flowshop, so M machine, and it's a permutation flowshop. So we want to find one permutation, and we apply this permutation on all the machines. So it's a difficult problem. So CDS builds M-1 dummy two-machine problems. I take an example. I illustrate this heuristic by an example. I take only 5 jobs. 4. 3 machines, and okay. So build n-1 dummy 2-machine problems, then solve each dummy problem by Johnson's algorithm, evaluate the sequence for the m-machine problem, and keep the best sequence. So what is the first dummy problem? I consider 4 jobs with a pseudo processing time on machine 1, pseudo processing time on machine 2, and the pseudo processing time on machine 1 is exactly the processing time on machine 1 of the original problem. So 7, 5, 9, 7. And the processing time on machine 2 is the processing time on the last machine. 4, 2, 10, 1. Then we apply Johnson. Johnson on this example gives what? We put job 4 on last position because it has the smallest processing time on the second machine. Then job 2 on the last position, then job 1, and then job 3. So this is, trust me, this is the sequence returned by Johnson's algorithm. And we evaluate this sequence with this data. So we put first job 3. Here I put now only the completion time of the jobs. So you have to be concentrated. Job 3, processing times are 9, 6, 10. So the completion time on machine 1 is 9, on machine 2 is 15, on machine 3 is 25. Right? Then we continue with job 1. Job 1, the duration is 7, 3, 4. 7 on machine 1, so the completion time on machine 1 is 16. Then 3, I take the maximum between 15 and 16, plus 3, 19. Then 4, I take the maximum between 25 and 19, 29. Okay? You got it? Job 2, 5, 8, 2. 5, 8, 2. And then job 4, 7, 11, 1. 7, 11, 1. This is the value of the make span. Okay? Then the second problem. For the second problem, for the pseudo processing times on machine 1, I make the sum of the processing times on machine 1 and machine 2. So 7 plus 3 is 10, 5 plus 8, 9 plus 6, 7 plus 11. And on the machine 2, I make the sum of the processing times on the last machine plus on the, not the last, but the machine just before. Okay, so 7, 10, 16, 12. And then I apply Johnson. Okay, here I put job 1 on last position. Then the smallest processing time is 10. I put job 2 here, job 4, and job 3. 3, 4, 2, 1. And again, I evaluate this solution with this data. Okay. I don't do it. We obtain a value and we keep the best value at the end. This is Campbell-Dudek-Smith. Okay, so here you have the definition of the pseudo processing times of the problem number R, and we compute Johnson for all this. We evaluate Johnson for the whole problem. Second heuristic is NE, Nawaz, N-score, and AM. It's a very, very famous heuristic for solving flowchart problems. First, we sort the jobs in sum of PIG increasing order. So if I take here this example, I do the sum. Here the total processing time is 14. Here it's 15, 25, 19. Okay? So I will consider first job 3, then job 4, then job 2, and then job 1. Okay? In this order. And for each job, I insert it at the best possible position. So I take job 3, and then I want to insert job 4, either before 3 or after 3. So I test 3, 4, and 4, 3. I keep the best. I don't know. I don't want to make the calcul. Okay? Suppose it is 4, 3. Then I take job 2, and I test 2, 4, 3, 4, 2, 3, 4, 3, 2. And I keep the best. And then I take job 1, and I try all the positions. And at the end, I have a solution. That's Ney algorithm. Very well-known heuristic in scheduling. Takes more time, but it's polynomial, so it's okay. Then you have the iterated greedy, proposed by Ruben Ruiz and Thomas Tutzel in 2006. It's based on Ney solution. You take Ney, the sequence given by Ney, then you remove some jobs randomly, and you reinsert these jobs at the best possible position according to Ney algorithm. And you have also an acceptance criterion, if you keep the solution or not, and at the end, you have a solution. And in fact, if Ney is the average gap of Ney is 3.35% in less than 1 second, the average gap of this heuristic is 0.44% in 360 seconds. So more efficient, but more time consuming. Okay, here are some references that you will have if you want more details. Now, basics on vehicle routing. Maybe it will be faster. I took some slides from Jorge Mendoza. It was very helpful for me. So some definitions. The traveling salesman problem, already defined, everybody knows. Okay. The capacitated vehicle routing problem is a generalization of the traveling salesman problem with a starting point, some nodes with a demand, and vehicle with restricted capacity, and you have to satisfy the demand at minimum cost. Okay. So first I will focus on the traveling salesman problem. And of course this problem is NP-hard. There are a lot of solution approaches, exact or heuristic. Exact methods are dynamic programming, branch and bound, in fact all the family of branch and something algorithms, constraint programming, and also constructive heuristics and meta-heuristics. I will only illustrate by some constructive heuristics, maybe the most intuitive methods. And the most intuitive method in this set of intuitive methods is the nearest neighbor method. The idea is to go to the nearest neighbor first, and then to the next nearest neighbor, and up to the end. And then you come back to the origin. And okay, this is very easy to implement. This is very intuitive, but it may be very bad, in fact. This heuristic is greedy. It makes myopic choices, and the result depends on the departure city. Here it's an example with 9 cities. Or 8? Yes, 9. 9 cities. Starting at city number 1 here. The tour is 173. And if you start at node 4, there is a tour with length 187. So worse. And if you start by node 2, you have a tour with 157, 58. Very, very good. So it really depends on the starting point. So it's not very good. This is an example where you can see that if you start with node 0, you go from 0 to 1 to -1 to 3 to -5 to 11 to -21 and back to 0. And if you start on the left in one line, you have the tour. So you can have a very, very bad tour or very good or optimal. So it's not very good heuristic. Some people have invented a method which is a pilot method. The idea is to build a solution by testing different local moves to evaluate the impact of each move and, well, to implement the best local move in order to obtain possibly the best method. So if I take this example, we start at city 0, and I will test the first neighbor, which is city 5. The evaluation of the tour is 172. And if I go now to the second nearest neighbor, which is city 1, I have a tour with 157. So I take the second choice, which is not the nearest neighbor, it's something else. And I continue. I am at city 1, I test city 5, and then after that, I will test city 2, etc. And I iterate, and at the end, I have a solution which is possibly better than a bad nearest neighbor. So at each iteration, we have two decisions, which city to insert and where to insert the city. It's insertion techniques. It's another type of heuristics. And for example, here we have a first tour composed by cities 1, 2, and 3. And for each other city, I compute two distances, the minimum distance to these cities, and the maximum distance. And then we can imagine several methods: nearest insertion, farthest insertion, 1, 2, 3, best insertion, etc., depending on the choice of the city and where to insert it in the tour. So we can imagine a lot of methods. Here it's nearest insertion, starting at, well, first starting with 1, 2, 3. First we insert city 5, then city 6, etc., and we obtain this tour. If we choose farthest insertion, we obtain this very strange solution. Then farthest insertion 2, etc. Okay, I don't give the details of all the methods. We can imagine a lot of insertion methods easily. Then we have also insertion techniques initialized by the convex hull. So you have to find the cities in the convex hull and then to complete the tour by using insertion techniques. And for example, here, with the nearest insertion, we obtain this tour. So as you can see, there are a lot of methods and a lot of possible solutions. Of course, all these methods are very quick. So one solution is to implement all these methods and to keep at the end the best solution. It's one possibility. Okay, for the VRP, vehicle routing problem, we have an input, which is a graph strongly connected, typically a complete graph, with a set of vertices, with 0 as a depot. All the other vertices are customers, and the set of arcs with a cost, non-negative cost or distances between two customers, and demands associated to the customers, and a set of vehicles with capacity. And the problem is to find a collection of circuits with minimum cost defined as the sum of the cost of the arcs of the circuits, such that each circuit visits the depot vertex, each customer vertex is visited by exactly one circuit, and the sum of the demands of the vertices does not exceed the vehicle capacity. And there is a huge family of problems in VRP: capacitated VRP, VRP with time windows, with black backholes, with pickup and delivery, etc., etc. So a lot of problems, a big family of problems in VRP. So to solve the VRP, it's at least as difficult to solve as a traveling salesman problem. In practice, it's considerably more difficult to solve than a TSP of the same size. You have some exact methods, a lot of exact methods, and you have also heuristic algorithms. There are MILP formulations, with arc flow formulation, set partitioning formulation, multi-commodity network flow formulation, I do not present in detail these models because it would be too long. So just I cite them, and there are a lot of heuristics. Apply simple and intuitive rules to build a solution, such as nearest neighbor, etc. Constructive methods, two-phase heuristics, improvement methods, and also meta-heuristics. And I think that you will have enough courses on VRP during the spring school, so I do not go into more details for this problem. There are also a lot of references, and you will have more, I think, during your stay in Troyes. So now I enter into the problem, which is integrated problem. What is the integration of scheduling and vehicle routing? Thank you for being still here up to now. So, as I said before, production and vehicle routing are two problems which are generally considered separately. The manufacturer produces, the production is stored, so there is inventory, and the production is delivered by another agent. That's the job of the manufacturer. And there is a 3PL provider who takes some items which are produced by someone else, and they are delivered to the customers. So that's what is done generally. We consider here that jobs are produced continuously. They have to be delivered to the customer within strict time windows, and vehicles arrive continuously to deliver the produced jobs. The first application we worked on was the production of chemotherapy drugs at the hospital of Tours. During the day, the chemotherapy drugs are produced continuously, and they have to be delivered to the patients for injection. For some of the drugs, the injection has to be done before 8 hours after production, so 8 hours mean during the day. But for some production, some preparation, it has to be delivered to the patient in 1 hour, in 2 hours, immediately, it depends. So in this case, you can imagine that production and delivery are strongly connected. Okay? And for this type of preparation, there are maybe 1 or 2 people who make the delivery. So they take some preparation, make the delivery, and come back. So the transportation time is not negligible in comparison with the production time of a dose. So we have to consider the problems in integrated manner. It's also the case for food delivery, fresh food delivery, because when something is prepared, it has to be delivered to the customer in a short time, because otherwise the customer does not pay. Okay? So I illustrate the problem with this example. We have some jobs, here 7 jobs, and you have a circle. The circle represents the location of the customer of the corresponding job. And the white, black in the middle is the production center. So suppose we have two machine flow shop, and we have to schedule the jobs and then to make the delivery. So imagine we schedule these jobs like this, so green, blue, etc. And we decide to make a batch with the 2 first jobs, and to deliver these jobs, first the blue, then the green, and then we go back to the production center. So it takes some time, and the vehicle comes back at a given date. At this time, either we can go with the 2 jobs which are already terminated, or we can wait for the 3rd job. And we have also delivery dates. Here we decide to wait for the 3rd job, and then we make the delivery of the 3 next jobs, and we have a waiting time of the vehicle due to the composition of the 2nd batch. Then the vehicle comes back very late, and at that time we can do the delivery of the 2 last jobs like this, and we obtain these delivery dates. Okay? So this is a solution of the problem. Of course, we can imagine another schedule. So jobs have different completion times. We can imagine different batching composition. So the jobs are gathered differently and the routing is not the same. So here we deliver the 2 first jobs, then the 3 next jobs, and finally the 2 last jobs. And the delivery dates, of course, are not the same. Okay? So, as you can imagine, there is first a scheduling problem. In which order can I decide to produce the jobs? From this order, we obtain completion times, so release dates for the delivery, in some sense. Then the batching problem. How do I group the jobs in order to deliver them? And for each batch, a routing problem. So in this sense, it's an integrated problem. And, je continue. Okay, and we have to do this, so to solve these 3 problems, in order to minimize one objective function related to the delivery dates. It can be the maximum delivery dates, it can be the sum of delivery dates, the sum of tardiness, the maximum tardiness, etc., as we define for the scheduling problems. Okay? So you can imagine the complexity of this problem. Of course, the data for these problems are very important. If we have very short transportation times, there is no problem. You produce, you deliver one vehicle, the vehicle comes back, you have not finished the next production, so no problem. In fact, no vehicle routing problem. There is only a scheduling problem. In the contrary, if you have very short production times, in fact, there is no scheduling problem. You decide the first batch, and then it's only a vehicle routing problem at the end. And the most complicated case is when processing times and transportation times are in the same range of magnitude. So we have the data as the data of a scheduling problem, plus the transportation times between 2 sites. Okay. The variables are the completion time. I call it the production completion time, and dj is the delivery time of job j. So 2 completion times, in fact, production completion time and delivery completion time. And then we deduce, we define the tardiness from the delivery time and not from the completion time. So we consider a problem where all the decisions are interdependent. With a scheduling problem, most of the time it's NP-hard. Of course, we can start with single machine problems, but still the problem remains NP-hard at the end. But one machine is generally more easy than flow shop or more complicated organizations. The problem is how to schedule the jobs. Then a VIP problem, how to deliver the jobs to the customer. And in this problem, of course, the problem of batching, how to gather the jobs into batches for the delivery. So in order to minimize an objective function and to satisfy constraints, we may have delivery deadlines. It's the case with the production of chemotherapy drugs. We have a deadline between the delivery date and the completion time. There is a maximum time lag between these 2 dates. The number of vehicles is limited, and the capacity of one vehicle can be limited or not. Up to now, we do not consider a limitation because batches are not big enough to take capacity into account. So the problem is clearly NP-hard, and the first relaxations are already NP-hard. So it's very difficult to propose efficient, exact methods for this problem, because if you try to simplify some hypotheses, you still have a difficult problem. You don't have a polynomially solvable problem, except if you simplify the problem too much, and at the end it's too far from the original problem. So this is supposed to be an example with 5 jobs, 2 machine flow shop, due dates, with I consider EDD sequence. EDD is intuitive. It's optimal for one machine. Of course, it is not for 2 machine flow shop because the problem is difficult. But anyway, it's intuitive. So let's consider EDD sequence. And then, as you will see, it's also intuitive to consider, maybe I can show it, yes. That's the schedule for EDD sequence for 1, 3, 5, 2. Then we consider two batches, 4, 1, 3 and 5, 2. And the routing, we consider that the routing is given by nearest neighbor. Why not? It's easy. So when job 3 is terminated, we deliver job 3, then 4, then 1. The vehicle comes back. And when the vehicle is back, it can take job 5 and 2 and deliver job 5 and 2 in the order 2 and then 5. And at the end, we have some delivery dates. And if we compute the tardiness, we obtain this quantity, 111, is the total tardiness with this very basic heuristic method. Okay, so only to fix the idea. Okay. So there is a lot of literature for this sort of problem. At a tactical or strategic level. For this type of problems, we have a huge literature. Thank you, Philippe. And the problems are related to factory location, deciding the production per periods of times, assigning customers to factories, decisions linked through inventory cost considerations. Always inventory costs are considered. And okay, so most of the time you have inventory considerations, quantities of production, quantities of delivery, but it's at tactical or strategic level. And for these problems, you have some survey papers. But we consider the problem at an operational level, at a detailed level. And for this type of problems, there is few literature. There is a paper from Shen in 2010 who proposes to a unified notation, extending the alpha, beta, gamma notation. But when you add more fields in the notation, it becomes more complicated, and people do not use it. So anyway, you can, if you want, adopt a notation for your problem with 5 fields. And about the delivery or shipping method, you have different possibilities to put in the field. And there is one possibility, which is routing. Routing means that batch delivery is done with routing. It means orders going to different customers can be delivered together in the same shipment. So vehicle routing is a part of the decision. So we can use this notation for our problems. So I don't want to read these small abstracts of papers. There are some papers working on similar problems with parallel machines, loading capacities. Here again, parallel machines, single vehicle with limited capacity, single machine, deadline, single vehicle, etc. So some literature start on this problem. You see the years 2014, 2015. It's not old literature. Lee et al. Bin packing problem with a fleet of heterogeneous vehicles, etc. Parallel production lines, etc. What we did, because we worked on this with Yannick and some other colleagues, we proposed the Mendel's decomposition algorithm for a parallel machine, plus one vehicle, plus minimization of maximum lateness. We also consider a two-machine flow shop with total tardiness minimization, and with the thesis of Azedin in 2017, we consider a single machine problem, single vehicle for delivery, a lot of particular cases, and also robustness considerations. So, some properties. Yes, question 1. May it be interesting to produce a job and to let it on the platform? It has not to put this job in the next delivery trip. Question. Is it interesting to produce a job and to let it on the floor? Suppose there is only one machine. We produce a job X and we do not deliver it. It means that we produce job X, then we produce a blue job, and we let job X here, and we deliver only the blue jobs. Is it interesting or not? Ah, yes, but you see, if we switch the blue job and X, we can start the delivery of the blue jobs earlier without modifying the delivery of the orange jobs. So in fact, there is no interest in this case. Okay? If there is only one machine. Suppose now we have a flow shop, and I consider this example, this very particular example, with job 1 and 2, which are the same jobs, processing time 1 on machine. It is a 2-machine flow shop. Processing 1 on machine 1, duration 100 on machine 2, these delivery dates, and X is 100 on machine 1, 1 on machine 2. It's very, very particular instance, of course. And 1 and 2 are at the same location, and X is at another location. Suppose you produce first X and then 1 and 2. Of course, X will be delivered on time, but 1 and 2, at least one of them will be delivered late. Suppose now you produce 1 and 2, and then job X. 1 and 2 will be delivered on time, but not X. So you have to mix 1, X, and 2. So we have to produce 1, then X, then 2. And now the question is, do we have to make consistent batches in some sense? Or is it interesting to let a job on the floor and to deliver the rest? Suppose we want to deliver 1 and then X and 2. Okay, we deliver 1, delivered at date 151, and then we deliver 2 and X. Of course, X will be late. Or 2 will be late, but some jobs will be late. Suppose now we deliver 1 and X, and then 2. In this case, job 2 will be late. And in fact, for this specific instance, the optimal solution is first to deliver X. It means I let job 1. I make the delivery of job X. And then, when the vehicle is back, I make the delivery of job 1 and 2. And then all the jobs are on time. And it's the only possible solution, the only optimal solution. So for this very specific instance, you can see that it may be interesting to produce a job and to let it on the floor, and then to deliver it later. It's not very intuitive, in fact, but it's still true. Okay, so it makes the problem more difficult than it appears, and it appears to be difficult. Maybe you know some things about split algorithm. I think you have heard about it today. So the question is, the split algorithm finds the best batching of items, assuming that the delivery sequence is fixed. So can we use the split algorithm to define the best way to deliver the jobs? Maybe it could be a simplification of the problem. Yes, that's true, but it depends. It depends because if we want to minimize the total trip cost, the original split works, it's fine. If you want to minimize the max span, or the maximum tardiness, or the total number of tardy jobs, number of jobs which are late, it's also possible to find the optimal batching by a split algorithm. But if you want to minimize the sum of completion times, it's not possible because the problem is NP-hard. So maybe you can use it, of course, but you don't have an optimal batching for a given sequence. You have only an approximate batching, except if you want to implement an exact method. But it's NP-hard. Okay, so it depends. So if you want to minimize the total tardiness is more difficult than the total completion time. The problem is NP-hard. So you can use a split algorithm, but only an approximate solution of a split algorithm. Okay. There are a lot of references on this. Resolution methods. You're still here? Okay. I will try to go faster. We will focus now on a two-machine flow shop, only one vehicle, and minimization of the total tardiness of jobs. And the model that I'm going to present now is the model that you will have to code tomorrow with GLPK. I sent you a model of GLPK with a flow shop problem, minimization of total tardiness. We add the vehicle routing part. Okay? So the data are this one, so number of jobs, number of machines, processing times, due dates, a big value, big M, and the travel times from seat J to seat G prime. What is very important to notice is that the production site is N. The jobs are numbered from 0 to N minus 1, and the machines from 0 to M minus 1. That's very important. If you forget that the production site is N, and if you think that it is 0, as we generally say, because it's easy to say that the jobs are from 1 to N and production site is 0, you will have some problems. So production site is N and the jobs are from 0 to N minus 1. We have the variables for the scheduling problems, YGG prime, the linear ordering variables. Variables for the batch composition, ZJK is equal to 1 if job J is in batch K and 0 otherwise. Variables for the vehicle routing problems, XJJ prime is equal to 1 if job G is delivered before job J prime in their tour, assuming they are in the same tour. And a lot of continuous variables, which are the completion times of the jobs on the machines, the tardiness, the delivery time, the starting time of tour K, and the finishing time of tour K. And with all these variables, we have the model. The scheduling part is the part that you already have and that I described some minutes before. So disjunctive constraints, linear ordering constraints, routing constraints, starting with C1J greater than P1J. Now the batching part, we say that a job belongs to one batch or tour by this expression. The starting and finishing times of tour are this one. It means that the starting time of tour K2, if K2 is greater than K1, is greater than the finishing time of tour K1. There is only one vehicle, okay? So only one vehicle for all the tours. A tour can only start when all the jobs are completed. So if job J is in batch in tour K, then the rest of the constraint is over, and you have that the starting time of K is greater than or equal to the completion time of job J on machine M-1. Then you have the VRP part with precedence between jobs. If two jobs are in the same batch, there is one job before the other. And to terminate the VRP part, I will give you these slides tomorrow again, okay? So the delivery date of job J is greater than the starting time of the batch plus the time to go from the source to, so from the depot and to the job J. And it's also greater than or equal to the delivery date of the job preceding J prime in the tour K. Finishing time of tour, tardiness expression, and then only the objective function, this one. Okay, so that's the MILP you will have to code tomorrow with GLPK. Maybe I will send you the slides before tomorrow, so you will have the slides if you want. Illustration by the same example as before. We obtain these values for the variables y01, 02, 03, 04 equal to 1, 131, 32, 34 equal to 1, etc. So the sequence is 0, 3, 4, 0, 3, 2, 4, 1. Okay. Then Z00 is equal to 1 means that 0 is in the first batch alone, In batch 1 there are job 2 and 3, and in batch 2 there are jobs 1 and 4. Okay? And x54 equal x41 equal x16. So the order is 4 before 1. That's for batch 3. And 52, 23, 35 equal 1 means that 2 is before 3 in batch 2. You will see this in details. This is the routing corresponding to this solution, and the total tardiness is equal to 61. Okay, that's the optimal solution. Given by the model, you will code tomorrow. Okay, there are a lot of resolution schemes. The exact methods are too time consuming for solving reasonable instances, of course. The first idea is to use construction heuristics. So you list the jobs according to priority rules. That's what I did when I say we sequence the jobs in EDD order. Then you build batches using a greedy algorithm, for example, and you sequence each batch either optimally, if the batches contain few jobs. Most of the times the batches contain very few jobs, so the vehicle routing can be solved optimally, or with a heuristic. We can also imagine an iterative procedure. We start with the first sequence of jobs. Then for this sequence, you find the best batching. And in each batch, you sequence the jobs in order to minimize the max span, because when the batch is known, what we want is to start as soon as possible. So what we want is that the schedule of the corresponding jobs minimizes the max span, whatever the objective function is. We want to leave as soon as possible, so we want to minimize the max span. So we can reschedule the jobs, and then why not reiterate with the batching process. Of course, we can use the wide range of meta-heuristic algorithms with local search, simulated annealing, taboo search, grasp, etc. You know these methods, I suppose. Examples of coding: direct coding of a solution. That's the coding that I propose in the Python file that I sent you yesterday. So it's a direct coding. If I take the same sequence as before, the first part of the coding represents the sequence of the jobs, and the second part of the coding represents the batching. How many jobs per batch and which sequence for each batch. In this very simple coding, you have a solution, in fact, immediately. And then you can apply a lot of neighborhood and the methods that you want for finding a better solution. Second type of coding, indirect coding with only the batching. You have only the composition of the batches, so one batch with job 0, one batch with 2 jobs, 2 and 3, not ordered, and one batch with 2 jobs, 4 and 1, not ordered. And then for 2 and 3, you have to define a schedule for these jobs, and also a route in order to minimize your objective function. You can imagine also another indirect coding with only the sequence of jobs, and then you apply, for example, a split algorithm to find for this sequence, this fixed sequence, the best batching and delivery for the jobs. It's heuristic. Of course, there are a lot of other possibilities. Okay, conclusion. We have seen what an integrated problem of scheduling and vehicle routing can be. We have seen some references. We have seen some resolution methods. A lot of problems have to be investigated in this field. It's an open field, so if you have some ideas, you're welcome. Most of the resolution methods have now to be invented, to be tested, in order to see what is the most efficient for these problems. And in the project part, you will implement the MILP model with GLPK and some neighborhoods in a taboo search algorithm in Python. And I see you tomorrow. Do you have any question?
So we have time for maybe 2 or 3 questions. Is there any question? Yes.
According to your experience, which is the best method for solving this kind of integrated problems? I mean, heuristics or meta-heuristics or?
I think also that the vehicle routing part may be solved optimally, because most of the time, because processing time and transportation time are in the same range of magnitude, the number of jobs in a batch is very limited. So maybe this part of the problem can be solved optimally. So maybe we can imagine methods with neighborhood search for the production sequence and coding optimally resolution of the VRP.
Have you included setup times?
No. So no, we don't. No, we don't have setup times. In fact, the real problem is not only a flow shop problem. It's more complicated than a flow shop. It's a sort of flow shop with batching machines. So machines that perform jobs simultaneously. It's for the part of the process which is called the sterilization of jobs. Then you have parallel machines. At the end, you have a control machine, which is unique. So there are a lot of constraints which are not presented here, and which makes the problem more difficult than what I said. But we don't have setup times. Of course, we can imagine problems for which we have to introduce setup times, maybe. But I didn't face to this constraint. Yes. Yes, the maximum number of. Yes. Yes. We can imagine a pre-processing which will limit the number of batches. Well, yes, absolutely. Yes, it will have an impact because it will reduce the number of variables and constraints.
A last question? Yes?
It will be done. It's a topic of the thesis of Alexei, who is here. He's working with the hospital, and we have to develop a dynamic version of the problem. We have already implemented a software in the hospital. The software makes the planification of the production, and we do not integrate up to now the routing part. And we have to modify this software to introduce the routing part. So it will be in a dynamic context. But it's not done at the moment. Thank you very much.
Thank you. He's not in my own laboratory. He's not at the head of my department, the laboratory. But I have also a gift for you, Jean-Charles.
Thank you very much.
Like Dominique. So the school is closed for the day. We invite you to organize your own session in some bar or some nice place to make a demonstration of P equal in P where you want. And we will see you tomorrow at 8:30 with a coffee. And we will start a new day with a new presentation.
Marc Sevaux.
Pardon?
Marc Sevaux.
Marc Sevaux, quoi.
Eh ben, c'est
Oui. The first presentation is the presentation of Marc Sevaux tomorrow. Okay? Bye and see you tomorrow with new speaker.